The nervous tissue is made up of a lot of neurons, and these neurons, they are not connected to one another. There is always a microscopic space, and this space is super very important in the communication. And this space or this gap is what we call the synapse. Good evening to you all. My name is Tumnad, and in today's video we are going to be looking at what we call synaptic transmission. Okay, so let's go ahead and get started and see what we call synaptic transmission. Okay, we need first understand what a synapse is. Okay, now a synapse is going to be that junction. Okay, it's going to be what we call a junction, or you may even call it a gap. Okay, you may even call it a gap, or you may even call it a space. Okay, we may even call it a space, and this space is going to be between two neurons. Okay, which is going to be between two neurons. Okay, so now that is a simplified definition of a synapse. Okay, it is a junction, a gap, a space between the two neurons which are going to be communicating to one another. Okay, we have a multiple of synapses, but now let us first classify them and see how we are going to be categorizing those kind of synapses. We have two classifications of the synapses. We have what we call functional. We have what we call functional classification, and then we also have what we call anatomical. Anatomical classification. Okay, so now let us look at one of them individually. When we look at what we call functional classification, okay, here we are going to be mainly focusing on what we call the mode of transmission. Okay, we are focusing on what we call mode. We are considering what we call mode of transmission. Okay, mode of transmission. And when we talk of mode of transmission, we have these synapses. We have the one which are chemical, and then we have those ones which are electrical. Okay, so now under functional classification, we are going to be having what we call chemical synapses. Okay, we're going to be having what we call chemical synapses, and then number two, we're going to be having what we call electrical synapses. Okay, so now let us briefly look at these two kind of synapses which are going to be under functional classification, which we are calling chemical and then electrical synapses. Okay, looking at what we call the chemical synapses. Okay, what we call the chemical synapse. Okay, chemical synapse. Now, when we talk about the chemical synapse, this is going to be the most common in the nervous tissue. Okay, it is going to be the most common. It's going to be the most common in nervous, system. Okay, it is the most common in nervous system. And with this kind of the synapse, it uses transmitters. Okay, it uses what we call neurotransmitters. Okay, and this kind of the synapse is going to be a bit slow compared to what we call the electrical synapse. Okay, we have what we call a synaptic cleft. Okay, we have what we call a synaptic cleft, and it is within this synaptic cleft that you are going to be powering our neurotransmitters, such that they cross stimulate what we call the postsynaptic neuron. The movement of the electrical messages is going to be unidirectional. Okay, the movement of electrical messages is going to be unidirectional flow. What do I mean by this? It means that the electrical message is going to be moving in one direction from the presynaptic neuron and then direct into the postsynaptic neuron. It does not come back. This one signifies that this is going to be a chemical synapse. Okay. These are some of the key features of what we call the chemical synapse. So now let's look at what we call the electrical synapse. Electrical synapse. Okay, electrical synapses. Now, the unique feature with these electrical synapses is that there is no physiological physiological. There is no physiological space. Okay, there is no physiological space in between them. Okay, but in the chemical synapse we have a physiological space which we are calling the synaptic cleft. But in these electrical synapses we don't have a physiological space, but we only have what we call gap junctions. Okay, we have what we call gap junctions, and these kind of synapses, they are going to be using the flow of ions. Okay, we are going to be using the flow of ions, and they are going to be fast conducting. Okay, they are going to be what we call fast conducting. Okay, they are going to be what we call fast conducting, and they are going to be mainly found in what we call they are going to be located in very many areas, but you can remember also this one. They are going to be also in part of what we call the cardiac muscles, and even also smooth muscles, what we call smooth muscles of intestines. Smooth muscles of the intestines. Okay, so now these are going to be the key characteristic feature which are going to be classic for what we call electrical synapses. No physiological space. There's going to be communication by use of ions through what we call the gap junctions, and they are going to be fast conducting. Okay, and then the last thing is that the flow of the messages can be either directions. It can be both directions, meaning that there is going to be bidirectional flow. Okay, there is going to be bidirectional flow. Okay, there is bidirectional flow of signals. Okay, those are the characteristic features of what we call electrical synapses. They are going to be located mainly in very many areas, like also the cardiac muscles and then the smooth muscle fibers of the intestines. Okay, so now let us look at now the second classification of synapses. And the second classification of some synapses, we said we have what we call anatomical. Okay, anatomical classification. So now looking on what we call the anatomical classification, here we are going to be looking at the axon terminal. It is going to be terminating with which part of the neuron. Okay, if an axon terminates on what we call the dendrites, then we also have that kind of the synapse, we have its name. Then it can also terminate to the cell body. It can even synapse also to the same axon. Okay, so now we are going to be having three categories of synapses under what we call anatomical classification. The first one is what we call axodendritic. Axodendritic, and this axodendritic, it means our axon terminal is going to be terminating with what we call the dendrites. Okay, here we are going to be having the axon. We are going to be having the axon terminating with what we call the dendrites. Okay, terminating with what we call the dendrites. That's what we call axodendritic synapse. Now, when you see this kind of the synapse here, it qualifies to be what we call axodendritic. Why? You see the whole of this structure here. This is going to be our presynaptic neuron, and this is going to be our postsynaptic neuron. Now we are seeing these kind of the dendrites. They are now going to be connected with this kind of the axon terminal. So now we have just cut the whole of that section having the axon terminal and then the dendrite. We have zoomed it here. Okay, we have zoomed it here, meaning that this kind of the synapse is going to be part of what we call axodendritic synapse. And because of this kind of this cleft, this synaptic cleft, it also qualifies to be a chemical synapse. Okay, it is such another beautiful thing. Okay, now that is our first category of the synapse under anatomical classification. The second one is going to be what we call axisosomatic. Okay, axisosomatic. And when we talk about axisosomatic, it means our axon terminal is going to be synapsing with what we call the cell body. Okay, and then the last one, which is very also very important, is what we call axonic. Okay, axonic synapse. And this one is very simple. It is going to be between an axon and again an axon. Okay, it is going to be between an axon and the axon, and that's why it is called axonic synapse. Okay, And we said that one neuron is going to be synapsing with multiple and multiple of other neurons. We have said that it can synapse on the dendrites, can synapse on the cell body, and even can synapse on what we call the axons. Okay. So now, having seen all that, the classifications. Okay. Now let's go ahead and see the synaptic transmission. Okay. So now, looking at this diagrammatic illustration, it is showing us this kind of the neuron, which is going to be now the presynaptic neuron. And then this one here, we have just brought in a very small part of what we call the postsynaptic neuron. But now we need to first know all these structures and how they are called before we go into really what we call the synaptic transmission. Okay, so now, if we don't want to congest this area, we are going to be just using numbers, and we bring it this side such that we see which part and how do we call it. Okay. So now, starting with this one here, this one, let it be part number 1. So now, our number 1, this one is what we call the axon, is what we call the axon terminal. Okay, is what we call the axon terminal. The whole of this structure here is going to be now our axon terminal. Now, coming to this one here, okay, these two channels are what we call, let me call them number 2. Okay, number 2, they are going to be what we call voltage. They're what we call voltage gated calcium channels. Okay, voltage gated calcium channels. Okay. And then you see the whole of this membrane here, this membrane is what we call, let me call it number 3. Okay, number 3. This is what we call presynaptic, membrane. Okay, what we call presynaptic membrane. And then again, this part number 4, this kind of the membrane. Okay, this is going to be now part, let me call it part number 4. Okay, so now this part number 4 is going to be postsynaptic membrane. Okay, postsynaptic membrane, and it's going to be part of what we call the postsynaptic neuron. Okay, and of course the whole of this one is going to be what we call the postsynaptic neuron. Okay, postsynaptic neuron. Why do we call it postsynaptic neuron? Because it is after the cleft. Okay, it is after the cleft, and we just call them pre or post depending on the location where they are. For the case of what we call the synaptic cleft, if it is before the synaptic cleft, we call it pre, and if it is after the synaptic cleft, we call it the post. Okay. And then we also have these other structures in this synaptic terminal. How do we call this structure? Let's call it number 5. So now our number 5 is going to be what we call, this is going to be our powerhouse organelle, which we call the mitochondria. Okay, the mitochondria. And then how about these structures? You see these structures which are going to be housing a lot and tons of what we call the neurotransmitters. How do we call these organelles? Let me call it number 6. Okay, so now our number 6 is going to be what we call a synaptic vesicle. Okay, if a synaptic vesicle. Okay, and then you're going to be having a lot of them. So now when we come to the postsynaptic neuron, we also have these kind of receptor proteins. You see this kind of the receptor protein, let us call them number 7. So now this number 7 will have what we call receptor proteins. Okay, and for the case of these receptor proteins, they are going to be having, you see this one here. This one is going to be now a neurotransmitter receptor. Okay, this is where our neurotransmitter has to bind if it is cause a change in this protein, which we call the ligand-gated ion channel. So now, in the case of the receptor protein, you're going to be having a neurotransmitter binding site. You're going to be having a neurotransmitter binding site, and then also we shall have what we call the ligand-gated ion channels. Okay, so now for the case of the receptor protein, we have the neurotransmitter binding site, and then also have what we call the ligand-gated ion channel, whereby the ions are going to be passing as they enter into what we call the inside membrane of the postsynaptic neuron. Okay, let me call this one the whole of this space. This physiological space, let me call it number 8. So now our number 8 is going to be what we call a synaptic, cleft. Okay, a synaptic cleft. Okay, then we also have these kind of proteins which are going to be located in what we call the presynaptic membrane. Let me call these ones as the number 9. Okay, and this number 9, they are going to be what we call reuptake. They are what we call reuptake protein. They are what we call reuptake proteins. We shall see their role after an electrical impulse passes. These neurotransmitters, they have to be taken off the synaptic cleft to avoid continuous stimulation. So these reuptake receptors or reuptake proteins are also super very important. Okay. And then we have this guy. You see this guy here? This guy is super also very important. Let me assign him number 10. That guy is very important. And that guy is what we call is an enzyme. Okay? Is an enzyme. He's going to be playing a very big role. Okay? And then you see these proteins which are going to be on the presynaptic membrane. And then also these proteins which are going to be residing on the membranes of these vesicles. So now these kind of the proteins, let me give them a name. Let me give them, like, for example, number 11. So now our number 11, I can just call them snare proteins. Okay, I can just call them snare proteins. Okay, and those ones which are going to be on the membrane, on the presynaptic membrane, they are what we call the T snares. We have what we call the syntaxin. We also have what we call SNAP25. And then these snare proteins which are on the vesicles of the neurotransmitters, they are what we call the V snares. And the classic example is what we call synaptobrevin. Okay, these ones are going to be aiding in what we call the pulling of these vesicles to fuse with the presynaptic membrane before they release their content into the synaptic cleft. It is also such another beautiful thing. Okay. So now, looking at now these structures and how they are called, let's go ahead and see how an electrical impulse is going to be crossing what we call a synapse. Okay, that is now our main target of today's discussion. Okay, so now let's go ahead and see what we call synaptic transmission. Okay, now, if we are to understand the synaptic transmission, the first thing to know is that we need to first have an electrical message coming to the axon terminal. Okay, that is always a classic first number 1 point to know. Okay, there must be an electrical impulse coming on this what we call the axon terminal. Okay, so now our first point is what we call action potential. Action potential arrives at axon terminal. Okay, at axon terminal. That is always our first point if we want our electrical message to cross this synapse. What else? When an electrical message reaches this axon terminal, a lot of physiological process happens. We have these channels which we call the voltage-gated calcium channels. These channels are going to open. The voltage-gated calcium channels are going to open. That's our second step. Okay? Our second step is going to be the voltage, what we call the voltage-gated calcium channel. Voltage-gated calcium channels are going to be opens. Okay, and now when they open, what happens? We are going to be having influx of the calcium. Okay, that is going now to be our third step. Our third step is going to be influx. Okay, influx is going to be what we call influx of calcium. Okay, influx of calcium into what we call synaptic, knob. You may even call it knob, you may even call it the bulb. Okay, meaning that our calcium is going to be coming inside here. Okay, it's going to be having entrance of what we call calcium. Okay, calcium is going to be entering this area. Okay, calcium is going to be entering. Okay, calcium is going to be entering. So now, okay. So now, what happens when calcium enters? Now, when calcium enters, we have these vesicles. We call them the synaptic vesicles. These vesicles are going to be containing the neurotransmitters. It is after the entrance of this calcium that we are going to be having now these synaptic vesicles going to be fusing with the presynaptic membrane, and then they release the neurotransmitters into the cleft. Okay, so now that's going to be our step number 4. Okay. So now that is going to be our step number 4. And our step number 4 is going to be what we call calcium. The calcium causes causes fusion of synaptic, what we call the synaptic vesicles with what we call presynaptic membrane. Okay, presynaptic membrane. So now when these vesicles now fuse with the presynaptic membrane, by the help of this snare protein, the likes of the syntaxin, the SNAP25, and then synaptographin, they are going to be pulling these kind of vesicles to fuse with the presynaptic membrane. This is what's going to be happening. So they are going to be having something like this. Okay, so now it means now our neurotransmitters are going to be starting to power in what we call the synaptic cleft. Okay, so now what next is going to be release our fifth step. Our fifth step is going to be now release of neurotransmitters. Okay, release of neurotransmitters. Okay, our neurotransmitters are now going to be released into what we call the synaptic cleft. Okay. Now, when the neurotransmitters are released from the synaptic cleft, they are going to be diffusing and then they bind on what we call the receptor proteins. Okay. We have what we call the neurotransmitters. This is going to be now our fixed point. Okay. The neurotransmitters, let me just use it for the case of short. The neurotransmitters diffuses, okay, diffuses across synapse or synaptic cleft, and binds on what we call receptor proteins. Okay, and of course we said our receptor proteins are going to be these ones, having what we call the neurotransmitter binding site and also what we call the ligand gated ion channel. Okay, so now if a neurotransmitter is excitatory, it is going to be what we call, it's going to be causing what we call a local depolarization. But if it is going to be an inhibitory effect, it is going to even to cause the postsynaptic neuron to even go into what we call hyperpolarization, okay, which is going to be now IPSP. So now EPSP and IPSP combined together are what we call the graded potentials. In other words, when the neurotransmitters bind on these receptor proteins, they're going to be generating what we call graded potential. Okay, generation of graded potential. Okay, generation of the graded potential. Okay, so now after we have generated the graded potential, remember the generation of graded potential is going to be happening on the dendrites and then also on what we call the cell body. Okay, so now if we generate the graded potential, that means we are going to be preparing for a neuron to fire an electrical impulse if a threshold value is reached. Okay, but if this graded potential doesn't reach the threshold, we cannot fire an electrical impulse at the axon hillock. Okay, so now let's assume that, for example, these neurotransmitters were sufficient enough and have caused the depolarization of this postsynaptic neuron and it has fired. Okay, our electrical message has now gone successfully. Do we need again these neurotransmitters to remain in the synaptic cleft? We don't need them. Okay, that means our last step is going to be removal of the neurotransmitters. Why? We don't want them to stay there because they are going to be keeping in what we call continuous stimulation, which we don't want. Okay, so now we are going to be having our last step, which is going to be step number 8. Removal is going to be removal excess neurotransmitters, and there are 3 ways how the neurotransmitters can be removed from the cleft. The first one is going to be what we call reuptake. We talked about these reuptake proteins, and then the second one is going to be, we see this enzyme is going to be also degrading some of these neurotransmitters. We have what we call enzymatic degradation. And then the lastly is going to be now the diffusing away into what we call the extracellular fluid, whereby it's going to be engulfed by one of the glial cell, which we call the astrocytes. Okay, it is also such another beautiful thing. Okay, so now our third mechanism is going to be now what we call diffusion. So now this is generally how synaptic transmission is going to be occurring in 8 steps. Okay, but There's something which is super very important. We need to know we have some neurotransmitters that are going to be creating what we call EPSP, or what we call they are going to be now excitatory neurotransmitters. Then we also have some neurotransmitters which are going to be causing IPSP on the postsynaptic neuron. Okay? So let's briefly look at what we call the neurotransmitters, and we see which ones are excitatory and which ones are inhibitory. Okay? And of course, our neurotransmitters, these are going to be the chemicals that are going to be aiding in the crossing of an electrical impulse. What do I mean by this? It means that here we're going to be having our electrical message in electrical form, but here it's going to be changed into a chemical form and then again converted back into electrical message. This is such another beautiful thing. Okay, for that reason, these neurotransmitters, they are going to be chemicals aiding in the transmission of an electrical impulse. Okay, so now we have excitatory and then inhibitory neurotransmitters. So now let's look at what we call excitatory and then also inhibitory. Okay, inhibitory neurotransmitters. Okay. So now the classic example of the excitatory neurotransmitter is what we call acetyl choline. If you have to forget other neurotransmitters that are excitatory, please do not forget acetylcholine as one of the major neurotransmitters in what we call stimulation of what we call contraction of the skeletal muscles. Okay, this is such another beautiful thing to know. Okay, another excitatory neurotransmitter is going to be what we call glutamate. Okay, is what we call glutamate. It is also such another excitatory neurotransmitters. Another one is what we call aspartate. Okay, is what we call aspartate. It is also one of the most beautiful neurotransmitter which is excitatory. Another one which is also very good is what we call histamine. Okay, histamine is also an excitatory neurotransmitter, and then maybe another one which we call the nitric oxide. Okay, we also have another excitatory neurotransmitter like adrenaline, but of course adrenaline and noradrenaline, sometimes depending, they can be inhibitory, even can also be excitatory. Okay, but these ones are going to be classic for excitatory neurotransmitters. Okay, so now let's look briefly on inhibitory neurotransmitters. The classic example of inhibitory neurotransmitter is what we call GABA. Okay, you have to remember this one as a must. If you have to forget other inhibitory neurotransmitters, please do not forget what we call the GABA. Okay. Another one which is super very important is what we call, okay, it is also one of the inhibitory neurotransmitters. And then another one is what we call dopamine. Okay, is what we call dopamine. It is also one of the examples of what we call inhibitory neurotransmitters. And then a last one is what we call 5-hydroxytryptamine. Okay, which you may even simply call serotonin. Okay, serotonin. You may even call it 5-hydroxytryptamine. Okay. So now these are going to be the classic examples of the neurotransmitters that are going to be causing inhibitory effect to the postsynaptic neurons, and then these ones are going to be causing excitatory effect on what we call postsynaptic neurons. Okay, so now but sometimes the existence of these neurotransmitters in the cleft, sometimes it is also very important. Okay, we're going to be having some drugs which are going to be blocking the reuptake mechanism. Okay, and this one, it is also going to be helping us in some kind of medical conditions. For example, if someone is depressed, depression is going to be characterized by low levels of serotonin. Okay, but now if we have a drug, if you can manufacture that drug that can block the reuptake of this serotonin, it means you're going to be trying to raise the levels of serotonin in the synaptic cleft. Don't you think it's going to be helping in elevating mood? Yes. So now we're going to be having some drugs. We have some drugs which are called selective serotonin reuptake inhibitors, and these drugs are classic important in blocking the reuptake of serotonin, such that will increase more of the serotonin in the synaptic cleft in a sense of elevating mood. It is such another beautiful thing. What are some of the examples of selective serotonin reuptake effect? We have what we call fluoxetine. Okay, what we call fluoxetine. We also have what we call paroxetine. paroxetine, okay? There are even very many other drugs. But we also have some other drugs which are not selective, but it can also inhibit the reuptake of serotonin, like for example, the tricyclic antidepressants, likes of what we call amitriptyline, okay? But of course, those ones, they are going to be not selective. They are going to be inhibiting a couple of the neurotransmitters. But these selective serotonin reuptake inhibitors, they are going to be only inhibiting the reuptake of what we call serotonin. They are all beautiful things to know, okay? So those are some of the ways of the drugs that can be helping us in what we call elevation in mood to people who are depressed, okay? So now they are also such another beautiful thing. So now this comes to the end of the study about synaptic transmission. If you think whatever I've talked is making sense, you are really benefiting, please make sure you like the video, comment in the comment section, share the video to whom you think is very important, and at the end of it all, you can subscribe. Thank you very much for listening. It has been Tumnad right away from the beginning up to the end, and of course Tumnad as always until we meet next time.